All right, guys, let me ask you a question here. Does the series this illustrates something to be very careful about. I like how you're all confidently saying the wrong answer. It's evil. If I asked you, does that sequence converge? Oh yeah, it converges to what? Yeah, it converges to 1/3. If you add 1/3 forever, does that converge? No. This is so freaking important. Note time. Sequences, you just have to look at them and see if they converge. Series, you gotta be a little careful. They don't mean the same thing, right? So let me see how I says it. The question about whether it converges is a very different question for sequences and series. Because series involves adding up all the terms. So if I ask you, do the terms themselves converge? Yes. But that's actually why the series doesn't converge. If a sequence converges, if a sequence converges to a number that's not 0, then the series diverges. You desperately have to realize that sequences and series are different things. Series takes sequences and adds them all up, so they look the same. But this tells you you're adding these terms up. What does the limit have to be so that it might converge? We've talked about this before. What's the limit of this have to be so that it might converge? Okay, yeah, it's got to be 0. If it's not 0, it definitely diverges. In order to maybe converge, it's got to at least have these elements go to 0. And we saw that. What did both of these? What does the sequence do on both? The sequence. What does the sequence do? Converges to 0. So they both have a chance to have the series converge. We know from what we said before and what we said earlier today that only one of those converges. Actually, only one of those series converges. You with me? If the sequence itself converges to something that's not 0, the series doesn't have a chance. It's got to converge to 0 to have a chance to converge. 1 over n didn't get out of its own way fast enough. And I don't know if I'd like to look at it that way personally. I don't know if you guys understand what I mean when I say that. It's exactly that idea of point 1. I know I keep doing this, but this illustrates that point so well. This gets out of its own way. So it's not actually getting a lot bigger. It's just point 1, 1, 1, 1, 1, 1, gets out of its own way. So 1 over n squared somehow gets out of its own way fast enough. So when you add them up, it actually converges to a number. 1 over n doesn't get out of its way fast enough. It does, the sequence goes to 0, but it doesn't get out of its own way fast enough. It actually overlaps and goes to infinity eventually. That's what that would mean for it to not converge. How are we doing so far? It's really, people confuse those so much. I see people looking here, well, it's 1/3, it's 1/3. No, it's a series. The sequence converges to 1/3, but the series has no chance. What's 1/3 times infinity? Infinity, right? So if I add up an infinite number of 1/3, that's infinity times 1/3, right? Ain't got no chance to be a number. It's going to be infinity. Okay, cool. So that's one little thing. Any other questions from stuff we've done? We got up through 11.2. You guys doing that? I'm kind of happy to see more people doing homework. I can see that in WebAssign at least. Right? There's actually more numbers and not just little symbols that tell me that they haven't looked at it yet. Right? So I can tell if you looked at it at least. All right. So we're going to get into section 11.3. We're going to answer that question from earlier. Trust me, I haven't forgotten. And this gets a little bit strange, a little bit weird. And actually, I want to pull up here the textbook. I think a lot of us don't have the text with us. I had it over.
Times 1 minus r to the n over 1 over r, 1 minus r represent?
That was a sum of geometric series. Yeah, so geometric one is the one that's based on multiplication. And the arithmetic one is the one that's based on addition. So many things to sit on. Same place, nobody's crazy. Let's see, so the textbook. Alright, so real quick, I want to show you a couple of pictures, because this gets a little weird, as you could probably expect most things will from here on out. Alright, so if you do have your book, section 11.3 now, so we're talking about the integral. So here's an example of 1 over n squared. This is the one that we know converges. So they've written it out for us. And what we start to do is you try to relate this to the integral. Because integrals are, of course, infinite sums of areas. So sure enough, if you look at 1 over x squared and you look at this integral, this first guy here is 1 over 1 squared. That area, right? The area of this one is 1 over 2 squared. So forth. Are you guys cool with that? This is just the old style before you even knew what integration was. This is how you would, the way you did it, right? And sure enough, when you integrate 1 over x squared, so I've got a series of numbers here that are all beneath this function. That's the key. This function itself, if I integrate it from 1 to infinity, it converges. Actually, let's see. We could do that very quickly, can't we? So I integrate that. How do you integrate that? What does that become? Let's see. We've got the t and all kind of business, I know, but just want to get to the point here. What do you get when you integrate x to the negative 2? So sure enough, when you plug infinity in there, what do you get? As you let this go to infinity, this is going to go to 0. So then you get minus, negative, so plus. When you plug a 1 in, you get 1. That's craziness. And that's, of course, from 1 to infinity, and then you add in the area of this guy, that's just 1 plus 1 is 2. So that's kind of like an upper bound for what my series does. Because obviously, if I integrate this, I'm going to add in a lot more area than there really is for my sequence, aren't you? Right, you guys with me? My sequence is going to be less than the integral of this. That feels like a comparison test. If I want to show that my sequence converges, I have to find something that's bigger than it that converges. So I can't go to infinity, right? If I want to show that mine diverges, I got to find something smaller than it that diverges and that pushes it out to infinity. So I like that ceiling and the floor idea, right? Okay, maybe. This is why when I look at 1 over root x, so they got the series 1 over root n. The reason that they did this one this way is because I have a feeling that that's going to diverge. Because of some of the earlier work we did. That would be a what power on the bottom? 1/2 power, which is less than 1. So then what we want to do then is find something that's less than this, always, that diverges. And sure enough, if I try to integrate 1 over root x, I end up with essentially root x. and that goes to infinity, right? When I integrate 1 over root x, don't I get basically root x minus a 2 in the right place? I'll let that sink in. Okay, all right. So when I integrate that, this integral of this would diverge since it's always smaller than my actual series. My series has also got to diverge. The floor pushes me up to infinity. So what we're actually kind of doing here is this is a not really a proof, but this is why it makes sense to use integrals to check certain types of convergence for certain types of series. There's got to be a couple of things that's got to be true for my series for this to work. The function that my series is built on has to be positive, always positive. It's got to be always decreasing, and it's got to be continuous. There. So it's got to be continuous, positive, decreasing. You guys sort of with me so far? So it makes sense. It's got to go to 0 or else there's no chance. Why would I even look at it? That would be the quick test. If I ask you, does this series, if I gave you this question that I had up here earlier, does this series converge? And it was up here, n squared over n squared plus 3. No work. You just say the sequence doesn't converge to. Well, I mean, the sequence converges to a number, it's not 0, so there's no chance. There's no work to show there. So I'm only going to apply the integral test to something that actually is going to 0, but it's got to do so from the positive side, and it's got to be always decreasing. And the two things that get a little bit of flexibility to them. Notice how everything here has 1 to infinity. You could put any number here to infinity and it still is true. Right? I don't care where I start. The idea of integral is still the same. So I could do 4 to infinity, 4 to infinity, so forth, right? So my sum was actually going from 11 to infinity. I can integrate from 11 to infinity. Okay, good. Maybe. Okay. What was the other thing I was going to... also, it doesn't have to always be decreasing. It just at some point has to be decreasing forever after that point. And we're going to see that a lot with series and with sequences. If I had a sequence that grew up into the billionth point, and then after that it shrank forever, then it's still going to be convergent. It's still going to go to 0, whatever, right? Just because it went really big for a while, it doesn't matter. It has to eventually get really small and go to 0 or go to whatever. Same thing here. It doesn't have to always be decreasing. It could go up for a while, but eventually it's got to be decreasing forever after that. So those are 3 conditions that have to be met that you have to show. Secondly, or thirdly, or whatever I'm in the list, the function that my series is built on, it better be something I can actually integrate. If it isn't, screw the integral test. We're going to learn some more tests in the later sections. Right? So the integral test is our first real apply a procedure test for series convergence. Right? That's our first one. There's going to be 4 or 5 more. So this is kind of nice. So here's an example of the thing that doesn't have to start at 1. So why is it nice that I don't have to start this at 1? Because it can't go through 3. Yeah. So, this doesn't really matter. They could have just put a letter A, a letter B here or whatever. It doesn't have to start at 1. It can start at almost anything. Okay. So a real quick example. They just take this guy. I mean, this guy. What would you use instead of integral test on that? Considering we know, what do you think about that example 1? It's probably going to do what? Okay, it definitely goes to 0, or else it's a very easy answer, right? If it didn't go to 0, the series diverges, I'm done. But yeah, you're right, it definitely goes to 0. What do you think that series is going to do? What does 1 over n squared do? Converges. And 1 over n squared plus 1 is dividing by even a little bit bigger than n squared. So it's definitely going to converge, right? What test would you use that we've already talked about? I wouldn't necessarily use integral test here, although integral test is pretty easy on this one. What would I use instead? Comparison test. Kick ass. I'll use comparison test. Right? But here they decided to use the integral test. The integral of that becomes inverse tangent. Plug your stuff in, you get a number. Yay. So the whole idea here is if the series converges, the integral converges. And vice versa. Right? Or if one of them diverges, the other one diverges. Period. Cool. Okay, maybe. So that's nice. That's kick-ass. They have a whole little thing here about the P thing we talked about already. When does that converge? So now let's do the one I was talking about earlier. All right, I'm done with this overhead thing. I want to look at the 1 over n ln. Because ln to me is one of the most interesting. You'll only hear a math teacher say something like this, but ln is one of the most interesting little functions ever. It's the bridge between negative powers and positive stuff, right? When you integrate x to the negative 1, you get ln. Thank God. But when you differentiate x squared, you get 0 eventually. There's no bridge, but ln kind of bridges the way between them. Also, ln grows so slowly. It grows slower than almost any exponent. So if I had this, let me see if you guys are with me on what's happening. If I had this, is that going to converge? Why? Yes, thank you, that's all. Right? What do you do with powers when you multiply like bases? Add them. Good. So that would be 1 over n to the 3/2. 3/2 is bigger than 1. That's going to converge. So I could put, right here, I could put 1 over 2, whatever. Will that converge? Yes. You kind of with me? That's kind of silly. It's such a hard edge right there at 1. It's insane. On one side it diverges. On the other side it converges. Right at it, it also diverges. And it's right a knife edge. So what's really freaky then is, relative to n to some power, what does ln do? Is it like square root of n? If it was like square root of n, this should converge, right? That would be like this. What I had up here earlier. So let's see. Let's try the integral test. What do I have to check to make sure I can use the integral test? And what do I have to be careful about? Let me be careful about right now about one thing. If I try to do it right now, at 1, this will be, yeah, exactly. So let's make this 2. Just to kind of illustrate that it doesn't have to start at 1 point, right? Yeah, how are you guys doing so far? Good? So I really want to see, I need to remember, I think I remember how this works. I do. What do I have to check? What 3 things? It's got to be continuous. It's definitely continuous, right, on its domain. It's continuous throughout this region here for sure. Positive. Certainly is positive. There's nothing in there that's going to make it negative. Right? And it's got to be decreasing. How could I for sure show that this is decreasing? Yeah, so we kind of know 1 over n. If you have a function you're not sure about, and you do a few, and they look like they're decreasing, you got to be really careful, because if you do a few and it looks like it's decreasing, you have no guarantee that it doesn't do this later. So if you had a function, this one's pretty easy to tell it's decreasing. The bottom is continuously getting bigger, so the whole thing is continuously getting smaller. But if you had a function you couldn't really tell, what would you have to do? How do we show something's decreasing in calculus? Let's take the derivative and show that the slope is always negative. There you go. Cool. So if I took this guy's derivative, after 2, it would be forever negative. Right? In fact, the integral test says at some point it's got to be negative. So it can be positive for a while, but eventually it's got to be negative forever after that. See, that's what you have to show. This one's pretty obviously decreasing. It's continuous, it's positive, so I'm allowed to use the integral test. So what would its associated interval look like? Let's start with integral.
From
2 to infinity. 1 over x. Good. We got to go to real numbers now, not just natural numbers. X ln x dx. Anybody have any clue how to do that? It's one we've done before. U sub, good. Because there's a function in there whose derivative is also in there. Yeah, so u equals ln x. du is 1 over x. So So we get integral 2 to infinity 1 over u du. And what's that integral? So we get ln of, I don't even need absolute values because everything's positive. ln of x evaluated from 2 to infinity. And technically I should have my little limits in here. Okay. Let me stop right there for a second. So one thing to realize here is, even though we're in the section that deals with sequences, series, all that kind of stuff, you'll never quite escape the integral. And you shouldn't look at it that way anyway. Integrals are there to be helpful. This is a place where they can be helpful. Now, as a student, you're probably going to be like, oh, shit. All right? I could put whatever I want to here and make you guys do whatever form of integration I want you to do. You have to know how to do it in the final anyway. I don't want to let too much time go between them, so I'm probably going to do exactly what I just said. You'll have some where you have to do by parts. You'll have some where you have to do trig sub. Who knows? Sounds great. So what happens down there? You'll get limit t goes to infinity, ln of t minus ln of 2. All right, so ln of 2 is just some number. What happens when t goes to infinity for ln of t? Goes to infinity really stupid slow, right? You guys see that? Is that cool? So what that says is, I want you to realize what that says. ln of n is effectively rising slower than n to any power, any small power, like the 1 over 2 quadrillion I had up here earlier, right? Just to make up a number. It rises slower than anything you can imagine that x does. That's insane. N to the 1 over 2 trillion, n to the 1 over 2 trillion to the 2 trillionth power. ln goes slower than that. Because these together, was it enough to make p bigger than 1? Because what does this do? What does it do? This integral does what? Diverges or converges? Shit. When you plug in infinity, when you let this go to infinity, what does this do? It goes to infinity. So, this integral, what does it do? Converge or diverge? Diverges. So therefore, by the theorem we just learned, the integral theorem, what does the series do? Diverges, because they do the same thing. This guy's integral and this guy himself, they do the same thing. If one diverges, so does the other one. If one converges, so does the other one. That diverges, so this diverges. So effectively, this is still on the order of n to the first power. Natural log of n didn't contribute anything to push him over that edge. You guys see what I'm saying? So I remember the day that I saw this, and I'm like, that is really freaky. Some of you guys are like, whatever, dude. But I'm hoping a couple of you might be like, yeah, that's kind of neat. That's kind of... It could be just me, and I don't care, obviously. I don't care. I'll be interested in whatever the hell I want to be. Life goes by much better that way. Let's see. All right, so the integral test is on page 716 in the book, if you want to look at that. They talk a little bit more about p-series, like we saw just a second ago, in there also. Blah, blah, blah. Oh, so here, let me give you this. That's right, I got another handout. So the very top of this handout is my reminder that when I ask you if a series converges or not, what do you check first? Yeah, make sure that the sequence itself converges to 0. If not, your answer is quick for the series. So please understand, I'm going to put at least one of those. Testing some poor person is going to be applying all these freaky-ass tests to it. You just need the most basic test. So what I want you to do is right in the middle. We haven't talked about the bottom yet. Right in the middle, try those out. We already did number 3. I forgot to put that on here. Number 1 and 2, you know the answer going in. So it's just to make sure that you understand how to set this up. So don't worry about number 3. We just did number 3. Don't worry about number 4. 4 is simple compared to what we've already done. Do 1, 2, and 5.
This just gives us a way to prove it. And actually, one way you can show it is by using limiters. But earlier, of course, we talked about every partial sum is bigger than this, and goes to infinity, goes to infinity. So we didn't do that. But that's another way to show it. Because we're adding this up. So eventually this becomes 1 forever. So what do you get if you add 1 forever? You get infinity. That's why the sequence itself has to go to 0 in order for the sum of those to be able to converge. If the sequence converges to any number that's not 0, it converges to 1 billion. If I add 1 billion to itself forever, it still goes to infinity and 0. Yeah, if I add 0 to itself forever, yeah, so you got to be careful. If the series converges, that doesn't say it's 0. If the limit is 0, it's minus. There's an example where the limit is 0, but it's not good enough. It's still divergent. I forgot that's from an old version of the book. So now look at page 691. It's from an old edition. Oh, be careful. Minus, negative, plus. But even it doesn't matter, as long as it the interval converges to some basis.
We gotta lift that on. So how's it going? Number 1, of course, you integrate, they get natural log. Natural log infinity is infinity, so yeah, it's gonna go to infinity. That's the divergence. 2, when you integrate, you get negative 1 over x. When you plug in t and let that go to infinity, that first piece goes to 0, but the next piece goes to 1. So that should become 1. The integral is 1. What does it have to do with the... Now, let me show you. I got a couple of faces that I don't like how to see. So when you, this is definitely positive, certainly continuous, and it's definitely decreasing. Just to cut to the chase here. So you get negative 1 over t minus negative 1 over 1. As t goes to infinity, this of course goes to 0. So you get 1. Now, what does 1 have to do with what this thing actually equals? It's definitely not what this thing converges to necessarily. In fact, I know it's not, because I'm using estimates of these rectangles that are always below this thing, right? So this is kind of an upper bound for what this thing is going to sum to. Let me say that again.
Saying like the area is 1.
Yeah, the area under this integral is 1. But that doesn't, you can't say anything about what this thing converges to. All you can say is this thing converges. You don't know that it converges to 1. You don't know that it converges to whatever specifically. You guys semi with me here? So be really careful. People sometimes take that to mean more than it does. As long as that number is not some sort of infinity, then I can say this converges. On what that number is, I don't care, really. It can be used for other things, but it doesn't have anything to do directly with what this sum is. How are we doing? This is a sort of an upper bound. But I got to remember that this particular one, this is why you got to be careful. This particular one had that large-ass big first one that we didn't even add in until later. So the 2 would actually be an upper bound for what that sum is. But we'll leave that alone. All right, how are we doing? So be short version. This number is finite. My series converges. If it's not, my series diverges. That's all you can say with any certainty. Cool. Okay. Let's see. Blah, 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 blah. What about number 5? What's the function look like that I'm working with? What's the summation notation for that? Yeah. E to the what? Thank you. Cool. So I don't know why I did that down there. Okay. Was it 1 infinity? Cool. So is this thing always positive? Yeah, because E is always positive and N is starting at freaking 1, right? So it's always positive. So good. Is it continuous? Yes, good. Any ratio of continuous functions is continuous everywhere. This guy's not 0, this guy's never 0. Okay, good. Is it always decreasing? Yeah. And now, would you make sure? Because the top is growing and so is the bottom, but obviously the bottom is growing faster, right? So to show it for real, what would you do? Can't use L'Hopital. L'Hopital only works when you're working with limits. Thank you. Good. This is not a limit. This is a straight up, what's the derivative? So I can show that it's decreasing. So how do I do that, guys? Derivative. This is a good place to get derivative practice. Yeah, I'd probably rewrite it like this. So you don't think it's quotient rule or something silly. So it's e to the negative x squared. It'll end up being minus 2x times x. Cool. And how do I show now? Now let's factor this. Let's see what happens here. For any number bigger than 1, which is when 1 or bigger, what's true about this term? Negative. So this derivative of this is always negative because this guy is always positive. Good. That's what's important here, right? Is what is positive or negative. This guy's always positive. After 1, which is where I'm starting, this guy is always negative. So overall, this derivative is negative. So this thing is decreasing. I just want to show you that at least once because you're going to have to do that for some of these functions that you just can't look at and tell. You're not always going to be quick. And on the test, I might ask you to do it no matter what. I don't care if you can see it. I'll say, show that this is decreasing using derivatives. Okay, so now I know it meets all 3 requirements, so I can do the integral test. What's the integral going to look like? Yeah, 1 to infinity. I might as well just write it like that, right? And of course, what's nice about this is not impossible, thank God. What method do I want to use here? U Sept, totally, because there's an x squared piece stuck whose x is down there, right? So if u is x squared, negative x squared might as well be. Du is so now I got my du e to the u du, e to the u, so e to the, from 1 to t, I might as well bring in my limit now. Limit. I'll let you guys absorb that. Is that cool? You guys see that? I'm not going to let these integrals for these tests get crazy because they're kind of like the second thing you're worried about. They're not the primary thing you're worried about. But they could be almost any form that we've done. Just got to be careful about that. This is just a nice straight up use of it. When you try to put, so now you get limit, t goes to infinity, negative 1/2 e to the negative t squared, plus 1/2 e to the negative 1. And of course, when you let t go to infinity, of course that first term is going to go where? 0, because it's to the negative power. It's 1 over infinity, basically. So that's going to go to 0. So I get 1/2 e negative 1, very specific number that the only thing that I care about is the fact that it is finite. It's not 0, but it's finite. So what does that mean about my sum? It converges. Cool. We would expect that, really, because, I mean, if it was n over n cubed, wouldn't an n cancel? It'd be 1 over n squared. That's going to converge. So n over e to the n squared, that thing is going to grow faster than almost any n's, any power I can imagine. You know, I mean, exponential grows damn fast. So that's like n over n to the 100th power or something crazy. That is definitely going to converge. It shouldn't be a surprise that it converged. Okay. All right. And you're all like, dude, everything's a surprise to me right now. So that did what? What was the answer? All right, let me see. Last little thing, and just to not be too technical about this. If doing this gives me some idea of whether it converges or diverges, something really important for this, especially when we get to like Taylor polynomials and stuff. I like the look on the face. If I'm trying to estimate something using a sequence, the whole reason I'm going to use, not even a sequence, a series. The whole reason I want to use a series is because I can write some ugly function in terms of a sum of easy functions. And the extra nice thing is, I only have to go out so far to be decently close to the right answer. So especially when we get to Taylor polynomials, we're going to really investigate the hell out of what I just said. But if I have a series that converges to something, all right, let's use the one I got on the paper there. What do we got? 1 over e to the 2n. Let's investigate this just by itself. Just go up to, if I want to go to infinity, but instead I actually just go to 4. If I just feel lazy, I don't want to go to infinity, let me just go to 4. Right? You don't have to feel too lazy to not want to go to infinity. Well, somebody help me out. The first 4 terms, 1 over e to the second plus 1 over e to the fourth. Just multiples of 2, right? So somebody help me out in the calculator. What is that? It's like 0.1. That's close. That's crazy, isn't it? Surprised myself. What is it again? Sorry.
15647.
15647. Okay, cool. So is that going to be what that really is? Obviously not, right? Because what did I stopped at 4. What is it? What's the series want to do? Go to infinity. Every term, though, is getting stupid small, right? 1 over e to the 8th by itself. What is that? 1 over e to the 8th. 8th, 256, 4.004. What is it? 000 something? Yeah. So it's getting stupid small. So it kind of makes sense. I should be able to stop somewhere because most humans don't care about the 17th decimal place. Some scientists do, so they have to go out to the 20th term, right? But most of us would probably only have to go out to the 4th, 5th, 6th term and get something reasonable. You kind of with me? So if let me see how it says. So if this is like A1, A2, A3, and I stop at A4, a good estimate, a way to estimate what the error would be seems to somehow involve the integral of the rest. So if I only go up to 4, so n equals 4, a good, let me see where I'm going to put this. A good estimate for what the error is going to be, this error for what I left out, would be integral from 5 to infinity. Right, n plus 1. So if I go up to 4, then the integral from 5 to infinity would somehow be involved in this estimate for what the error is. You guys kind of with me? No, okay. Let me show you from the book. Better pictures always make it better. Okay. So if you got your book, this is on page 718. And by the way, that reference on the handout that I gave you, page 619, I think it is, whatever that is. See the reference to the textbook in there somewhere? It's from an old, different calc book. I don't even know if this book does what that book did. So I'm sorry, I forgot to update that part of the handout. There we go. So if you have your book, look on page 718. So, I mean, here's the rough idea. If I integrate from n to infinity, that's going to be smaller than what's left over. If I integrate from n plus 1 to infinity, that's going to be more than what was left over. So then the error must be in the middle of those two, integrating from n plus 1 to infinity and n to infinity. So if I do those two integrals, then I'm going to capture the error in between them. So a very quick example. Let's do the example I got there. That's crazy. There it is. So if you didn't have the book, I just wanted to show you that visual real quick. And both of these are the same exact height. Just one of them starts at n and the other one starts at n plus 1. I want to be able to capture my actual sequence elements here. So if I start at n, I have to use the right endpoint. If I start at n plus 1, I have to use the left endpoint. I don't know if you guys... If you're not careful with reading this over, you might think this is sort of cheating somehow, but they have to capture these actual values. So you can't alter the height of this. So that's why one is left end and one is right endpoint. But the idea is still there. If I integrate on either side of where I stopped. So if I look at this sequence here. So we stopped at 4. So then I want to integrate. What are my two integrals going to be that bound my error, my remainder actually? Where am I at? Okay. So my f of x is 1 over e to the negative 2x. Is that cool? It's my f of x. What's this integral going to be? So I want to know what are the remainder for, oh shoot, I always forget which side it's got to be on. Oh yeah, that makes sense. It's got to be, oh yeah. So I want, if I use, so n is actually the n I use. So we used 4. That's what I forgot, if it was like the next one or the same thing. So if I use 4 to estimate it, then I want to know the remainder for only going up to the 4th sequence element. Yeah. What happened? Is it okay? What's up? Okay. So this would be from what? So infinity. 5 of e to the negative 2x dx. And this, of course, would be 4 to infinity. Right? And this is a nice integral. I've talked to several of you one-on-one, and I think in general, e to the ax is always easy to integrate. How do I integrate it? What do I get? Itself over the negative to kill it. And I want to go from 5 to t, where t goes to infinity. Right? This one is the one that's less interesting, the lower bound. I'm mostly interested in how big my remainder could be. So very often you'll only have to look at this guy. Does that make sense? I want to know how big my error, how much could it be off? Not, here's the least you could be off. I want to know how the most I could be off by. Right? So I'm going to capture that remainder between these two integrals. All right. So once I got one, I got both of them. So when I plug a t in, I'll get negative e to that. It's going to go to 0. Is that cool? Because this will be over this, going into infinity. The whole thing is going to go to 0. Just want to try to cut to the chase and get out here on time. So it'll be minus negative, so it'll be plus e to the negative 2 times 5 over 2. And this side, very similarly, it'll be e to the negative 2 times 4. Somebody help me out. What is that? What's e to the negative 10 divided by 2? I always wait for somebody to go, you should know, man. You're the math guy. What the hell is it? 0.000?
4 zeros.
4 zeros? What about this one, e to the negative 8? Divided by 2? Oh, 0, 0, 0, 0. Okay, and this is 0, 0, 0, 1, 6? Yes? Okay. So that's the most I'm off by. If I only go out 4 sequence elements in my series and add those up, I'm off by at most this. And I know this is the absolute bound. In fact, I'm probably off by less than this because this is the absolute most it could possibly be. So if you can live with that error, you would only have to go out 4 elements for this sequence itself. Some sequences you have to go out further. Some you won't have to go out very far at all because they get small really quick. Yeah.
Can we just keep it in the sign?
Sure, yeah, of course. Yeah. That's plenty. It's got to be plenty because that's it.